Hi everyone, so in today's video we're going to be talking about solving connected body problems. So in today's video we're going to be looking at three of, I would say, the most common connected body problems in grade 12 physics. So if you're able to understand and solve all three of these problems, you should be fine to solve any connected body problem in the future. So let's take a look at this first question. It's asking, there's two objects of different masses connected to a pulley, connected by the same rope. So for these types of problems, the first thing you want to do is find which way your system is accelerating. So over here, we know that the acceleration is going to go in this direction here, because it's obviously going to accelerate where the mass is greater. So of course, because it's heavier that way, so it's going to accelerate that way. The second thing is we need to establish our free body diagrams. So I'll do that over here. We're going to do one for each object. So for object A, we obviously have the force of gravity, and then we have tension force going upwards, just like that. And if you're wondering um, what these small subscripts mean, sorry, one sec. Okay, if you're wondering what these small subscripts are, this just means force of gravity of the Earth acting on object A, or the force of tension of object B acting on object A. So it's a little confusing. If you don't like to look at it this way, you don't have to use the subscripts, but that's just how I was taught to do things. Okay, so this is object A. I'm going to set Y to be positive in the top direction, and then for B is going to be the same thing. So it's gravity. This time is going to be the Earth acting on B, and tension would be A acting on B. And I'm going to put these ticks here to signify that the tension force is equal for both, because it's the same rope, so there's the same tension force. Okay? And also notice how I've drawn the arrows. I've drawn this arrow here to be a bit longer than this one because there's greater mass for object B, so it's going to have a greater force of gravity. So the longer the arrow is, the greater the force. Okay, second thing we need to do is establish equations. So with these types of problems, you want to establish equations for each object and for each direction. So like X or Y direction. For these problems, this one in particular, there is no force in the X direction, so we're just going to ignore that part and just do in the Y direction. So I'm going to write the sum of forces in the Y direction for object A, which is going to be the tension force minus the force of gravity. And this is because the net force in the Y direction, of course, is going to accelerate in the direction that the net force is in. So because object A is going to accelerate upwards, we know that the tension force is stronger than the gravity force. So that means you have to subtract the tension by gravity. Okay. And then this is going to equal the net force, which we can also write as the mass of object A times acceleration, because we know that F(et) equals mass times acceleration. That's the first equation. The second one is going to be for object B. This time, however, it's going to be the gravity force minus tension force, because we know that since the object is accelerating downwards, the gravitational force is stronger than tension. Okay, so now we have all the equations established, and what we're going to do is we're going to treat these like a system of equations, just like you do in math. So I'm just going to number it for clarity. And you'll notice here that the tension forces actually cancel out, which makes perfect sense because it's the same rope. So the tension force is really negligible when we're trying to find acceleration. So anyways, you can cancel those out. When we add the two equations, it's simply going to be gravity of B minus gravity of A, and then equals this plus that. So this is our final equation. What we're going to do now is we're going to expand these open and put it into terms where we can actually substitute values in. So because we know that gravitational force is just mass times gravity. So this is going to be the mass of B times 9.81 minus the mass of A times G. And here I'm actually going to factor out A because we're trying to solve for A, so this is going to make it easier to isolate for. And now we can just plug in our values. So this will be 600 times 9.81 minus 400 times 9.81 equals acceleration times 1,000 kilograms. And then you would just solve this as usual, just like you would solving normal algebraic expression, and you should get 1.96 meters per second squared. And then our direction, it's just going to be the same as these arrows that we've drawn over here. So it'll be upwards for A and down for B. Okay, so now we're done the acceleration part. We also have the question asking for tension in the rope, which is really simple. All we're going to do is we're going to use the acceleration that we found and plug it into either one of the equations. So, for example, I'm going to use this equation over here. Know that Ft of B on A, you don't have to write the B on A part because tension is really the same for both. It doesn't really matter like which object is acting on the other, but you can keep it if you want. And then minus gravity of the Earth on A, and then ma times acceleration. And now we're just going to plug in values like usual. This again is just mass times gravity. So this is going to be 400. 400 times 9.81 equals 400 times 1.96. And then if you solve this correctly, you should be getting the tension to be 4,709 newtons. And then the direction is actually going to be up for both. So you need to be careful here because, okay, A is the same as before. But B, you can see how the arrows has flipped. This is because the tension force is opposite of the acceleration that it's going in, right? Because the rope obviously is up here, but it's accelerating downward. So that's why you have to be careful and make sure it's plus. It's going upwards for B. Okay, so that was question 1, a fairly simple question. And now let's move on to another problem. This is another pretty common question that you'll see. So, like before, we need to establish the direction the acceleration is going in. So this will be going down. And then objects. I'm going to call this object A and B. So yeah. So now free body diagrams once again. For A, we obviously have force of gravity. And then we also have normal force from the table, which is pushing against the gravity. So Fn of table on A, we have tension force pulling this way. B is acting on A. And then we also are told that there is some friction here. So we also need to account for that. Friction will move in the opposite direction of the acceleration. So that's why the arrow is going to the left. Also, just put this quickly. Okay. So this is a force of kinetic friction of the table on A. I'm also going to add these ticks because the gravitational force is equal to normal force. Okay, and then for B is going to be simpler. It's just like the last problem. We only have gravity and tension force upwards. And then I'm going to put these ticks here because tension force is equal for both, since they're both connected by the same rope. And then once again, we're going to set up our equations. This time, object A will have two equations, one for x and one for the y direction. So let's start with x. In the x direction, acceleration is moving to the right or towards the tension force. So it's going to be the tension force minus the friction. And this is actually going to equal to the net force, and I'll say, you'll see why later. So this is normal minus gravitational. And this is actually going to equal 0 because we know that the box, there is no acceleration. There's no vertical acceleration in the box. It's not jumping up and down. So that's why we can put this mass times acceleration over here because that's where all the net force is going. Okay, and then for object B, we only have force in the y direction. And this is going to be gravity minus tension because the gravitational force is stronger than tension. Okay, and then once again, I'm going to number these equations. I'm going to call the middle one 3 because it equals 0 and it has a bit of a different use. And then once again, so I'm going to just say, ignore this part for now. That part is going to come in later, but for now, we're only going to pay attention to equations 1 and 2. Again, you can cancel out the tension force and then add them together, and then you'll get this equation. Gravity minus kinetic friction equals the net forces added up. And there we go. So now once again, we need to split these up into terms where we can substitute values in. So this is going to be mass times gravity minus, if you recall, the force of friction is the coefficient of friction times the normal force. So here's coefficient of kinetic friction, and then our normal force. Well, how do we find that? This is where equation 3 comes into play. So if you can't already tell from the equation, if you rearrange some stuff over, you can see that the normal force is equal to gravitational force. So they balance each other out, and we know that gravitational force is the mass times gravity. So we can actually just treat the normal force as the gravitational force. So we can just multiply this by mass times gravity. And then again, I'm just factoring out A. And then we're ready to plug in our values. So B is 1 times 9.81 minus coefficient of kinetic friction is given to us, 0.23 times 3 times 9.81. And then this is 1 plus 3 kilograms. So now you can plug these values into your calculator, and you should get an acceleration of 0.76 meters per second squared. The direction is going to be to the right for A and down for B. So there you go. So that's for the acceleration. Now it's also asking for tension. So once again, we're just going to, I'm going to use equation 2 this time, just because the mass of object B is 1 kilogram, so it's a bit easier to work with. So I'm going to rewrite it over here. I'm not going to put the subscript this time because tension really is the same for either way. And now, just like before, you just plug in values. So it's going to be 1 times 9.81 minus force of tension times 1 times 0.76. And you should get 9.05 newtons. And then the direction, once again, right for A, and then up for B. So please be careful with the direction of the tension. Once again, these are actually flipped around. Okay, so that's yet another very standard problem. So make sure you understand this. And we're going to move on to the very last problem. This one, I will say, is the most challenging of the problems, but it is still really common because we have this incline here actually. So we need to account for that. So if you feel confident, you can pause the video and try it yourself. I'm going to dive right in. So very first thing, as before, we need to determine acceleration. So this bucket is going to accelerate. It's going to accelerate down. And then this block is going to move up the ramp. Let me make that square. Okay. And then once again, we need the free body diagrams. So I'll draw that over here. So for object A, we can see the object A is actually on a slant. So what we're going to do is we're actually going to set up the coordinate system to be like this, on a slant as well, because it's going to make things a lot easier for us. So once again, gravity is always there. It's always pointing downwards. And now we have normal force here, which is pushing it up like this. So we're actually going to draw it diagonally, like that. That's normal force of the ramp on block A. Okay, and then we also have tension force pulling it this way. And lastly, we have kinetic friction. There we go. So we're actually not done yet because it's going to be really helpful if we see here this force of gravity, it's like compared to our coordinates here, it's on a slant, but it's going to be a lot easier for us if we turn it into the same direction as our coordinate plane. So I'm actually going to make this longer because it might get a bit messy. So I'll just draw this a bit longer. What we're going to do is we're actually going to make dotted lines like this, because now we can account for gravity in the y direction and in the x direction. So this is going to be 35 degrees as stated in the problem. And if you look at this is a right angle triangle, so we can actually just use basic trigonometry to figure out what the two vectors are going to be. So cosine. So, okay, let's look at the y direction first. So it's adjacent and hypotenuse, so that tells us we're going to use cosine. So then in the y direction, it's going to be this, cos theta. And then since sine is the opposite and hypotenuse, this x direction is going to be sine theta. Okay? And there we go. That's everything we need for the free body diagram of object A. Object B is a lot simpler and a lot less scary. It's just up and down. So gravity and tension. Okay, so I'm gonna set these equal, and these should also be equal, and yeah. Okay, so we're done our free body diagrams now. So we'll move on to the next step, just as before, which is establishing the equations. So let's start with x force for object y. Sorry, for object A. So the reason why these free body diagrams are super important is because it might get a bit confusing because we have so many forces. So drawing it out makes it a lot more clear. So for x, we have these arrows here. And we're just going to look for arrows that are parallel to the ramp. So that's going to be these three forces. Because a lot of people actually forget to put this gravity force here. Not that one. This one. A lot of people forget to put the gravity in the x direction. So we've drawn it out to help not forget. So because acceleration is in the direction of the tension force, as we see here, it's going to be tension minus the friction force minus gravity in the x direction. Another way to look at it is you can just add these together because the friction and gravity are acting in the same direction and then tension is in the opposite. So you can think of it like this if it's more clear. And this is going to equal mass of A times acceleration. And then in the y direction, this is simply going to be normal force minus gravity in the y direction, so cos theta, and this is going to be 0 because once again our box is not moving in the y direction at all. And then for object B, there's only force in the y direction here, so it's just going to be the gravity minus tension because it's accelerating downwards. And this is going to be mass of B times acceleration. Okay, so once again, this equation is going to be neglected for now, unfortunately. And we're just going to look at equation 1 and 2. So just like before, I'm going to rewrite this and I'm going to expand equation 1 so to get rid of the brackets. I'll just leave that part out actually. So tension minus friction minus gravity equals net force. And then we're gonna write equation 3 here. So gravity minus tension equals net force. And then we can cancel out the tension forces like we did before, and then just add the two together. So it's going to be gravity minus friction minus gravity in the x direction equals these added together. And then let's just expand these three out. So mass of B times gravity minus coefficient of kinetic friction times normal force. And then remember, just like the previous question, our normal force actually equals the force of gravity. So we can just say that the normal force is mass of A times G. So mass of A times G minus, this is also mass of A times G times sine theta equals, factored out again, there. And now we can plug in our values. So, what's the mass of B? Mass of B is 40 kilograms times 9.81 minus mu, which is 0.123 times mass of A, which is 45 times 9.81 minus 45 times 9.81 times sine 35 degrees equals acceleration times 85 kilograms. Okay, so it looks like a lot, but we're just gonna plug everything into calculator. And if you've done this correctly, you should get 1.11 meters per second squared. In our direction, it's going to go up diagonally for A, and then B is going to be accelerating downwards. So that's the first part. We found the acceleration of the entire system. Now let's move on to question 2, which is asking for tensional force in the rope connecting the two objects. So this is very simple, just like before. I'm gonna pick equation 2 and plug in the values to solve for Ft. So this is just gonna put here minus FTAB equals mass of B times acceleration. So then this is gonna be the same as before. I'm just actually gonna leave the subscript out again because it doesn't really matter which direction it's going. And then mass times acceleration. And then last but not least, we're just gonna plug in these values. Mass of B is 40 times 9.81 minus T times 40 times 1.11. Now plug this into your calculator and you should get 348 newtons. And then the direction, this way for A, and then up for B. Once again, be careful of this. And that is question 2 done. Oops, what did I do? Okay, we're done question 2. Lastly, we have question 3 to deal with. Question 3, we're actually going to use kinematics for question 3 because it's asking for block A's displacement, and we're just going to use one of the kinematic equations. So just like we normally do, you would write all your variables on the side. So we're looking for displacement. The initial velocity is 0 meters per second because over here in instant 1, it tells us that block A and the bucket are momentarily at rest. So that's going to be 0 meters per second. Our time is 2.50 seconds because it tells us now that it's 2, it's sliding up for 2.5 seconds. And then we also have the acceleration, 1.11 meters per second. And now we can just use one of the kinematic equations. We're going to use this one that doesn't have final velocity. This is 1/2 acceleration t squared. And then this can actually cancel out because our initial velocity is just 0. And now we can solve for displacement. So half of 1.11 times 2.5 squared. And you should get 3.47. What are the units? It should be meters. I'm just going to put meters for the units. And then it's going to be up diagonally this way. We don't have to do it separately for A and B this time because the question is only asking for block A's displacement. So make sure you read it carefully. So that's all. We just need to do that. And that's the final question. So we've got all 3 questions answered. This one is also very common. So make sure you study this one well. And yeah, that's it. So thank you for watching.